Hello and welcome to episode 216 of Quarkus Insights. We're going to be talking about Leyden, and we've got a special guest who's Andrew Dinn. So welcome, Andrew. And before we jump into that, we do have some news as well. So we've been busy with releases. So we're working towards Quarkus 327, which is our next LTS release. And so we've released 326, which is going to feed into, we've branched 326, that's going to feed into 327. So we released 326 last week. And so I'll share the blog for that in the chat. It's got some Hibernate updates. It's got named persistence units in Hibernate Reactive. You can have MCP functions sort of running through the dev UI, which is quite cool. So that's 326, and we have also done 327. Oh, sorry, not 327. We've done 326.1. So we did an emergency release immediately after releasing 326, because as well as all that good stuff in 326, we picked up a vertex regression, which we then did an emergency fix on the vertex side and an emergency fix on the Quarkus side. So we also have 326.1. So if you're picking one of those up, we would recommend 326.1. So there's the release notes explaining all that. So now that we've got that out of the way, I guess we can jump into Leyden. So before we start with Leyden, actually, perhaps could you introduce yourself and your involvement with Leyden and the JDK?
Okay, so I'm Andrew Dinn. I am a Red Hat Distinguished Engineer, only I now work for IBM, as we've all moved to IBM, but I'm still a Red Hat Distinguished Engineer. That's my title. I've been working in Red Hat and IBM since 2007, and I started working on the OpenJDK project about 2011. I sort of slipped in under the radar. And worked on the ARM port of OpenJDK. Andrew Haley and I basically made OpenJDK work on the new 64-bit ARM hardware, actually before the hardware was available. That was like my first big task on OpenJDK. It was quite a task. It was great fun. Since then, I've been working on the virtual machine mostly, working on various areas of the virtual machine. And I worked on Quarkus also, helping get the Mandrill downstream of Quarkus, a stable, releasable, maintainable version for Red Hat. And as part of that, saw some of the virtues and also some of the problems of ahead of time compilation of Java, completely ahead of time. And obviously, the benefits of very fast startup and better application warm up. And this was something that clearly was a problem with OpenJDK, where because it does everything lazily, you have very good peak performance when you've warmed up, but it can take a while to start the JDK runtime itself to get to application main. And application main can take quite some time before all of the methods that a server's running or whatever the application is are actually running at their peak performance, because it slowly compiles and optimizes, and it uses the interpreter at first to see what's running and then speculatively optimizes on the basis of what it's seen, which gives it phenomenal performance, but it takes a long time. So we were wondering if there's a way we could get some of the benefits that you get in GraalVM for quick startup by having some work done in advance. And I sort of agitated about this and lobbied people in the Oracle side of the OpenJDK project. And eventually Oracle came back about 2 years ago, and they'd already been working for a while, and they'd actually got a sort of prototype of a project that they set up called Project Leyden, which didn't really have an activity for the first year, but they were busy beavering way behind the scenes, and they've actually come up with something that really does help application start warm up and also JDK startup. So about a year ago, I started getting involved on the coding side with that. I freed myself from other commitments, and I've been contributing along with one of my colleagues, Ashutosh Mehra. We've been contributing quite a significant amount to the project. It's actually looking at this issue of how can we take some of the stuff that Java does lazily and do it ahead of time in such a way that we can actually avoid work that happens exactly the same time every time you start at the JVM, and just have it all ready in advance from a prior run. Now, that's a dangerous thing, because you've always got the possibility that work you did during the prior run can actually be inappropriate when you come to do your production run, because something's changed in the environment, or the command line arguments have changed, or you've got a different class path and so on.
Yeah,
So,
which I guess is why we didn't do this 20 years ago.
Absolutely. It's been tried. There's been lots of attempts to try and save and reuse, compile processed bytecode in the form of class metadata, compiled methods. Every time it's failed because it's really hard, and it's really hard to keep it consistent. In fact, this is one of the things that was an issue with GraalVM. GraalVM has this clever substitution mechanism that allows you to plug a JDK runtime that's built to run on the OpenJDK JVM on top of a lightweight, ahead of time compiled VM called Substrate VM. And they have to do that because the internal APIs between the Java code and the JVM have changed, because that Substrate JVM is actually written in Java. So you've got to change some of it. It's very different when you've got a VM written in C++. So they had this mechanism that allowed them to change the way some of the things behaved. And it allows you ahead of time, if you process code, to actually end up running different code in your production run than would have run if you'd ran on the JVM. It's a very powerful mechanism. It allows you to compile a lot more stuff ahead of time, but it also risks you running code in a way that differs. The semantics of the code differ. The values of static fields can be different. Even the actual way the code executes, it can execute with different logic with this mechanism they have. So although it was a very good mechanism that was necessary to allow you to completely ahead of time compile everything, it had the disadvantage that it could introduce subtle differences. And those had to be whack-a-moled out with a hammer repeatedly. It happened. And I'm not saying that it doesn't now have clean semantics, or at least for the JDK itself, it does. They work very hard to do that. But because you can use a bit of building ahead of time for application code, it's possible that middleware or application classes can run into this same problem. And it's because the mechanism they have is very powerful. So in Leyden, we've tried to get a sort of intermediate approach where we are much more careful about what we do up front and what we prepare up front to avoid this problem of any possibility of incompatible behavior. Even to the point that if there's an object that you could create at runtime and you create it at ahead of time and store it in a heap image that you pull in to populate the heap, you've got to be sure that the identity of that object isn't going to be something which could influence the behavior of something else in a way that would depend upon this environment at build time, and could be something that would have been compiled in a different way and have a different object identity because of the way things were developed at runtime. So we've got very, very stringent requirements to make sure that the semantics are exactly the same. And therefore, we've done less ahead of time compilation. But there's also a reason why we're doing less work ahead of time, which is we want to have stuff that we can load, information about the class base, information about bits of heap objects that we can have pre-prepared and linked into the classes as static field values or whatever, information about compiled methods and actually compiled code. We want to have some of that, but we don't want it to have to do everything ahead of time like GraalVM does. We don't want to have a closed world where you've got to define the whole code base. We want a runtime which works as it currently does, where you've got stuff that's all pre-prepared, but you can still load code dynamically and still load classes dynamically. You can compile stuff dynamically, and it can update and re-optimize code that you built ahead of time. So it's a hybrid between ahead of time preparation of some of the code base and runtime development and optimization of the rest of the code base. It's a sort of sweet spot between fully at runtime that OpenJDK does, and fully at ahead of time that GraalVM does.
And how narrow is that sweet spot? Because I know one of the things that, and probably, one of the sort of the motivations for Leyden was that we had this binary between you had to do everything the JVM way or you had to do everything the GraalVM way, and you couldn't sort of try and have more of a spectrum. And so is Leyden just a third point on that spectrum that's quite fixed, or does Leyden allow you to sort of go along the slider?
Yeah, how elastic is the amount of pre-work you can do? Well, so what's this really interesting, we've actually had Leyden for a long, long time. It was called CDS. So CDS and application CDS, which was the thing before CDS just became, it's all CDS, was an optimization where instead of reading in all the bytecode for all the JDK classes, or even for application classes that are in the class path, and translating them to the internal model the JVM uses, you could preload all of the JDK classes, or if you run with app CDS, the extended capability that we now have as a default in up to 24, you could actually preload all the bytecode and build a model of what the JVM would like as its representation of the class base. No parsing required, therefore. Save that to a CDS archive, and when you run afterwards and that CDS archive is there, map it into memory. It's all there in the right layout for you to know ahead of time which classes are in the JDK and what they look like as individual classes, but a whole suite of all of the JDK classes or some of your application classes as well. And so that bypasses the need to do a lot of the work of processing bytecode, building an internal model of the class base. And that's been around since JDK 13, I think. So it's a technology where a small part of the stuff that you need in the runtime could be built in a pre-run, and in fact, it comes bundled with a JVM. But the JVM build process runs Java and builds a CDS archive. It's already there with the release. That's a sort of the minimal Leyden, and it's a very narrow little window. You've bypassed some of the work of processing the bytecode and processing it to build the class model, not to process the method bytecode and compile code or any of the other things that the bytecode's used for. But you throw away all the stuff about class structure. You just keep method bytecode after that. You don't need all the rest of it. So that's been around for a long time. Now, what we've done is we've added more and more stuff. We've widened the window of things that you can prepare in advance. And we've also made it possible for you to use them throughout the process rather than just up front at the first load. This stuff can be used repeatedly to continue answering questions for what do I have here? What can I do? Can I just quickly do this step without having to do all the work? So we broaden the window of which it applies. And that means that we're optimizing not just JDK startup, because you've got answers to various questions during the JDK warm-up before you get to the main. But we can also answer information for the application and say, here's some stuff you need now, just have it and do things with it. So we've got more things we can answer questions about. And we're actually delivering that capability with 3 main JEPs. So there are 3 ways in which we've really extended CDS to add new performance improvements.
And do you think, I'd love to hear more about the JEPs and the sort of that staging of delivering. But before we go there, and this is actually sort of a future question, like a way future question. But do you think that window will ever become so broad that Leyden starts feeding into GraalVM, and then they sort of start to become more synergistic?
So I think there's a possibility, but I think it's unlikely, because what we're doing with the Leyden work is we're deliberately targeting these resources that we're building ahead of time for a VM whose operation is fundamentally dynamic.
Yeah,
it's capable of loading new stuff that's never been seen before. And so it's built around a virtual machine mechanism, a model that expects to have to add stuff to accumulate more stuff over time, and also to rebuild stuff that we built, to recompile code. Because we may have a compiled version, but we find we go down a path we've never hit before, because it was never hit during the original runs. And so we do what we normally do in the JVM. We de-optimize that method, jump back into the interpreter, and meantime in the background compile a new version of the method that includes the bytecode for that path that we just ignored. Now, the reason we have that capability is because if you ignore bytecode on cold paths, you get much less bytecode to compile, you can inline much deeper, you get many, many more optimization opportunities. So one of the reasons why the OpenJDK compiler is so efficient is that it can work out in advance. I don't need to look at all this stuff. I've got a very narrow window of code that is the stuff that's going to be run. I'll compile that and simplify everything and then optimize the hell out of it. So this ability, if you go off path at runtime, to jettison the code and recompile it, means you can retune the VM to deal with unexpected cases, but you win by having code available right away because it's pre-compiled that you can load and run and get the benefit of. So we're getting a mix of the best of both worlds. We don't have to compile every time. We don't have to run in the interpreter for a while to get to compilation, but we can still recompile. But that means we're built for an engine that's got that capability. Now, the GraalVM engine is built to have everything worked out in advance, optimized as far as possible, really brilliantly optimized to be as small and as efficient as possible, but it has to cater for every possibility. You can't go down a cold path. So you've got to compile in every possible option. You can try and compile a narrow version of the code, but you have to have a fallback pre-compiled that will deal with the, oh, I've gone off-piste problem. And it's got to be there in advance. And the whole virtual machine mechanism is built around having those decisions already made. So they're very different machines, and it's really hard to take the optimization process for one and reuse it for another. There'll be some synergies and some ways both can learn from each other. We've learned things from how GraalVM does stuff, and also from the attempt to do AOT compilation back in JDK 14-15 using the GraalVM compiler in OpenJDK. But they're really not going to be the same sort of thing.
Yeah. Yeah, makes sense. So sort of, I guess then, stepping away from speculation about the distant future that may not even make sense, what's for those JEPs, sort of what's been done, what's coming?
So we've delivered 2 of the 3 main JEPs that are planned for the extensions to the CDS model that saved class metadata and avoided the work of building the class model. Now, the CDS archive and the class metadata is basically an in-memory representation of the class base that you've encountered during JDK startup or during a CDS application run where you've loaded application classes. It's in a format which, instead of being bytecode, which is very dense and is difficult to process and to index, it's unwrapped into a structure that you can interpret fast and you can run compile code off fast. Because if you need to refer to the class base to say, what's a super of this class, you can find it really quickly and really simply. So it's an in-memory model, and you can save it, dump it and restore it in memory format and get your code base, your class base, fine. But it's an individual class model. Each class has its own structure and its own information about the layout of that class, its methods, its fields. But classes actually cross-reference each other. So in the constant pool of class foo, you might have a reference to string.class. In the code, the method could say, is this class of this object equal to string.class? That's a reference to a Java object that actually is independent of foo.class. And the metadata model has to be supplemented at runtime. When you try and run a code and you refer to string.class, you've got to go and find the metadata model for string in the class model, find the Java heap object that represents string.class, and then link that into foo.class so that foo and its code can say, is it equal to this? And string.class will be there from the startup because it's put in as one of the bootstrap classes by hand, in fact. It's very carefully constructed during setting up the spinning plates of the VM. But if it was foobar.class, you might not even have foobar.class loaded. So when a method tries to refer to foobar.class, you have to go and see if the class is there first. And if necessary, load it, link it, resolve it internally to itself, add it to your class base, and then cross-link. Similarly, if you want to call a method of an object and it turns out to be an instance of a foobar, you've got to go and find the method on that class, and then the call site where you're about to either interpret or compile a call has to be set up so it can actually find the relevant method code and execute it. So this linking happens all the way. When you first load your classes, you start running a bit of code. Every now and again you stop and you say, oh wait, I've got to find if this class is there. I've got to find a static field and work out where it is in memory. I've got to access a field of this object. I need to know what offset it is. Is it the first, the second, or the third word where that field's stored? The first time you run an operation like that, you dive out in the VM, update the metadata to keep track of all these information about where methods are, where offsets are, and then you carry on. Next time you try and access a field, you've already got information, you cache that, and you don't do it again. But it's quite an interruption to the execution. And so you can actually prepare some of this stuff in advance. And that saves a lot of stopping and sidestepping, jumping out of hot code into the VM and back again during startup of the JDK, during warm-up of the application. It applies both for JDK classes and for application classes. So if you can pre-link some of this stuff in a prior run, and everything turns out to be exactly the same class, linked in the same way, you can already have all these links in place. And that was the first thing we added to the CDS archive to extend it. We added class linking. That went into JDK 24.
And what's the trade-off there? Is this something that everybody should be enabling all the time, or is it something that sometimes it helps you and sometimes it doesn't?
Well, it's probably something that you would get a benefit from almost all the time. But it might be that you, in order to get this to happen, you have to run your application, and the application has to exercise code that calls methods, that accesses fields, that creates class, references class objects and so on, that call, this is actually where the real payoff is, that calls a Lambda that needs a method handle to be created by running a bootstrap method. The method handle object creates a method type and a method form in the heap, are attached to a thing that represents that method, attached to an auxiliary class that holds the Lambda body. So there's actually heap data created when you link a method handle. All of those things are susceptible to saving. You pretty much get a win, except that if you run in your training run, you run loads of Lambdas that are only part of your training setup. And then when you're in your production run, you don't run them again. You've got a load of Lambdas that you sort of pulled in and a load of data in your heap. And you won't pay any cost for running them, but you might have stuff that you don't need there. But mostly you'll probably need this stuff, because if you used a Lambda in training, you'll probably run it to do some sort of, you'll have a provider or a supplier that you use in production. So most of the time, this pre-linking is a really big win. And particularly, instead of stopping running a bootstrap method to give you a method handle, linking it into some heap objects, building it into the compiled code and the interpreter, if you have that available, that's a massive win. And every time you do a string concatenation, you have a method handle created to do the concat. And that's fine, it's quite efficient. But having it pre-created means it happens instantly, rather than having to do it with a one-off initialization of the method handle. The repeated concatenations don't cost you, but that first one does. So it's a really big win to have this linking pre-done. And we think that probably gave us about sort of 20% improvement on the startup, something like that. We're in the Spring Boot Pet Clinic app, for example, and we're getting, just with that optimization, we're getting about 20%, 15-20%. There's more to be got as well on startup, and similarly, there's also warm up gains, because if that helps the JDK startup, it can also help your application startup.
Yeah, and so you mentioned Spring Boot. So of course, since this is Quarkus Insights, if for a Quarkus user, what's the sort of the integration with Quarkus like?
Well, so we've had a talk with Georgas, who did the CDS integration, because you've got much the same issue as you have with app CDS. You have to run your application using Leyden to build a cache that has the pre-linked classes in it. And then you've then got to rerun your application in production with that cache in place. So there's a two-step process. You train the application, and then you run with the cache that's produced at the end of training. And it's very much like app CDS. You need a model where you can actually, when you're developing, build your cache in one run and then test it out by actually running it. So the mechanism that's already in place has been modified to deal with that issue. But there are a few more wrinkles, because when you run your application with app CDS, you basically just run the application, load your classes, and at some point you get the application modified so that you've got a switch that enables it just to exit early. And whatever classes you loaded by them, they've gone into your class base. Now there's a bit more to do with a bit more complexity with Leyden, because you actually have to run code in order, for example, to get the linking benefits. And we'll see with the later changes we're adding, there's more imperative to run code. You actually have to run code in order to access fields, to invoke lambdas, to call methods, so that you actually build this linkage structure into the class base. And when you've done that, we then save all that information about what's been linked, and we can then build a CDS archive or an AOT cache archive now off it, which includes our linkage information. So you can't just load your classes and that's it. You've actually got to exercise the application. And the more you exercise the application, the more things there are that we can save into the archive. But of course, that means you either run the full application and then you're running live with instrumentation going on, and you can have an issue with it slowing down the actual run. And also at the point where you want to save things, you've got to stop the application and dump an archive. and you may not be happy about having your application stall for however long it takes. It may be only 10 seconds. It may be maybe a couple of minutes if it's a big archive, if you run and train for a long time. You don't really want to do that. So you probably want to train it offline, but in that case, you've got to have synthetic data. You've got to actually run it up to a point where you can somehow tell it to stop. And it may be easy just to load your classes and then stop. But if you want to load your classes, run a sort of simulation of the application and somehow have a way of making it exit, it's tricky. So we've got several models for how you can control this. And I think the one that's been used in Quarkus is just to have the application have a switch which says, I'll just exit now. So you can basically run until the application exits, and you save all the information you've gathered about what it's run and build the archive at the point where it exits. And one of the other options we've had is someone from Microsoft we've been working with, as Matt Carter, has built a mechanism where you can use a J command, the J command messaging app that talks to the VM, send a message to the app to say, dump your training data now. So you can run it for a while, and then from the command line say, I'd like you to stop now and dump an archive. So that's another way of controlling it. You can also, he's worked on a prototype mechanism which I think is in the Leyden archive now, where the Leyden repo, where you can say, if you hit this method, at the point where this method is called, or where it's called for the 5th time, whatever, at that point, dump the archive and then exit. So there's several different mechanisms we can use to trigger the archive creation, but you've still got to set up a sort of either a live run or a dummy run simulating behavior that will exercise your code in a way that will actually allow information to be gathered about how it runs, so we can do these optimizations.
Yeah, and so then, yeah, I see what you mean. So it's sort of an operations challenge then as well.
Yeah.
Of trying, because when you were initially talking, I was sort of wondering why we didn't just integrate with the cloud providers and have it so that you could just harvest from your live runs, and then you explained the several disadvantages of doing it that way. But then,
yeah, and it's particularly that you've got to stop and dump an archive, and there's quite a lot of information to be dumped. More so as we talk about the other jets, where we've added saving and restoring of more information. But the other challenge, obviously, is when you've dumped your AOT cache in a training and assembly run where you build the cache, you've then got to install that into a deployment container, if you can use a container, where it's used in the production run. And as far as the class model linking is concerned, there's nothing that's architecture specific there. But the other things we've added that are giving more optimizations are actually architecture specific. And also, even with the same architecture, you might run the JVM with different command line configurations. And those command line configurations can mean that the information in the archive is invalid. If you save an archive where you've got compressed oops and you try and run without compressed oops, the heap objects that are in the archive are compressed. And you try and load it into a heap where you've got uncompressed pointers, they're incompatible. So we fiddle things so that we always process stuff using an uncompressed model. But there's other configuration parameters where we can't change things at the moment. You have to have exactly the same hardware capabilities and mostly the same JVM command line options at the point where you create the archive and at the point where you run. So you can't build them on your desktop Linux box, x86 box, and deploy on a souped up Xeon processor that's got all sorts of capabilities. It just won't work because it's not compatible. Yeah. This becomes more of an issue with saving code and restoring code as well.
How sensitive is it to architecture? Is it just sort of a x86 to Xeon sort of thing, or is it going to be that if I'm on a T2 micro and then I go to a T2 medium, I'm doomed?
It's at the moment we're disallowing any real variation in the hardware. So you basically need to build the cache on the production hardware.
Yeah,
we're actually working towards having more flexibility. You can build on hardware, possibly reducing the capabilities to get something that's a sort of vanilla build that will be compatible with most hardware, and then deploy in a hardware that has more capability. Obviously, if you do that, it doesn't affect the class layouts, it doesn't affect this linkage model, but when it comes to saving and restoring information about compiled code, which is where we're moving towards in the next JEPs, it's going to matter, because if you compile code that uses a capability like AVX3 on Intel, or the equivalent vector capability on ARM64, and then you run on hardware that doesn't have that, if you've got compiled code that's used those instructions, they're going to fault. because it's just not appropriate. And it's not just the vector hardware. There's various other hardware capabilities that can vary, that if you build an older hardware or weaker hardware and deploy in more powerful hardware, you'll get away with it. But if you do it the other way around, you're in trouble. But it's also true if you switch garbage collector, that's a problem. If you've got objects that are built and for a model expected by a given garbage collector, and you build code with garbage collector barriers in, you can't then run it in a heap where you've got a different garbage collector and different barrier code for the compiled method code. So there's more issues about incompatibility down the line. What we're trying to do is find ways of compiling code ahead of time, which we can reuse where we bypass these. We'll talk about more when we talk about the compiled code JEP, which is the third JEP. But we will try and minimize these disparities so that you have more flexibility at build time of what you build on and what you use as command line options versus what you use in the runtime. I mean, one of the things that does work, for example, you can compile, you can run with one of the compilers only in the production run with, say, C2 compilation, and compile C2 methods, heavily optimized methods in your building training run. But you can actually use those C2 methods in a runtime where you've only got C1 methods, or we even have the compilers disabled. So for people who don't want to do any compilation at runtime, they can still compile methods during the training run, save them in the archive, and get the benefit of those compiled methods, but basically not do any more compilation. This is a niche area that Alexei Shipilev is very interested in examining, because some of the Amazon customers who do high frequency stuff don't want any compilation there, but they would love to have compiled code in advance rather than just doing a little bit of compilation and switching off the compilers, which they do now. They really don't want any compilation, but they want the compiled code, and instant compiled code is even better. So there are certain things where things do work and people are interested in the trade-offs there. And that's the thing we're still investigating. We're not clear about all the trade-offs, which is why some of the stuff that we're doing, the last JEP, the compiler JEP, is being delayed till 27. And some of the benefits will only really manifest in 28 and then eventually 29.
How idiot-proof is it in terms of so is it a case of sort of write once and test everywhere and hope you don't get a seg fault? Or if I do it wrong, will I get a really clear message saying
you should never get a seg fault because of Leyden. One of the things we've done is been very conservative about what we're willing to put into the archive. Not just the metadata, the linkage data, but also information about compilations and what we're willing to do with the compiled code. We've been very careful to make sure we don't build in something where you get an error. Obviously, it can happen, and there will be bugs as we iron this out, but we're playing on the very cautious side. So none of this should ever break. If the worst comes to the worst and your archive has something incompatible, we will jettison the archive and run without it and build everything dynamically, because we've got a dynamic VM, so we can just load stuff and compile stuff. That's the benefit of having this. If the archive has any flaws or is a mismatch with production, we can still run. But of course, you might see a production hit because your warm up and your startup are both a bit longer, or a lot longer. And the better we get at doing Leyden, the more you don't want that to happen. So we can think of more and more optimizations to put in, but we've also got to be very careful we don't put in optimizations that could poison the archive for a deployment, and then you don't get any win. So we're still experimenting with the trade-offs here. And that's again why we haven't gone for the compiled codes save and restore in 26. We're putting it off to 27, and we're going to do the tuning and the tweaking of the trade-offs in 28 and 20, and then eventually have those ready by 29. We really see 29 as an important target to have most of it working with minimal perturbation and the ease of use issues addressed, because that's an LTS release, and that's the one we want to hit. We got the 25 that did give a good improvement. But we really want to see these next set of JEPs giving us the really big improvement that will make the biggest difference.
Yeah. And so in terms of the roadmap, sort of, if you had to say like a proportion of the benefit available now and then like.
It's difficult to know because we don't know how far this is going to go. And although we will have something that will give we think that we will get. We've already in certain applications seen a 40%, 50% reduction in startup time, time to JDK main, to entering the application main. And we've seen in some examples getting to peak performance can be cut by about 20%, the application warm up possibly more, but we haven't experimented enough to know for sure. But we've already seen examples where the application is hitting its full throughput rate 20% quicker than it would have done. So we know already we've got something that can give us really significant improvements, but it's all about the detail and about the tuning and balancing of things. So what the two checks we've still got left, this is an example of this. The first thing we've actually got in 25, saving of compiled method profiles. So when you're running your application, you run in the interpreter first off, and then you compile to using the C1 compiler to have code that's instrumented to keep track of what's being executed. And when you've got all this information about how it's run, that gives you a lot of tips about which code gets run, which is hot, which is cold, which things you can ignore. It tells you about which types of arguments you've seen, so that you might expect to have a foo, but it's always a foo bar. So if you're going to compile a method there, it's a virtual call, you just call the method a foo bar. You don't bother with calling the generic method with a generic dispatch. You go straight to foo bar, and as long as it's a foo bar, you do a quick text, you're through. So, we've got all this information that we build up, and we save that in a thing called a method data object. It's a method profile with profile counters and some method counters for the number of calls, which the interpreter populates. Those are being saved into the archive now. Now, those are what feed the compiler. After you've got the profile, you first of all C1 compile without instrumentation to get a quick, fast version of the method. And if it's called enough times, you then say, oh, this is a really hot method. We're going to C2 compile this. We'll spend quite a lot, maybe 4 or 5 times as much time compiling as a C1 method took to compile, but we'll compile the hell out of it and really heavily optimize it. And all the profiling information you've got allows you to really quickly compile something to really incredibly fast code. And if you de-optimize because you hit a path or you get an argument type you weren't expecting, you can recompile it, and you've got all that information there to recompile and get back to fast code that's really, really optimal very quickly. That's being saved in the archive. Now, it's the other half of that is to save the code that went with it, whether it was C1 code we generated in the training run or C2 code. You really want to save that as well. And we didn't have time to get that in. But the profile information gives you a benefit. It's already there with JDK 25. When you start up, you haven't got any compiled code, but you already know which way to compile it. So methods you've got profile information for from your training run, because you compile them during the training, you can just start compiling them straight away. You might as well, because you know they were hot. They're very likely to be hot in this run. If you compile them in the order they got compiled last time, you probably deliver the compiled code at about the same rate as it was delivered during the training run. So your methods will pop up ready compiled just at the point where you're going to start interpreting. You actually want them to pop up just a bit earlier, because you had to run in the interpreter first. You just want the compiled code right now. And it's probably exactly the compiled code you want, because most methods just run and don't de-optimize. They're the best code right at the start. And they satisfy all the things you're going to do in your run. So this is a good optimization, but we're still having to do the work of compiling things. And actually the danger here is that we've got all these compiled method profiles. So we set a compiler to running full pelt, compiling everything. Meanwhile, we're trying to start up the JDK, and then we're trying to warm up the application. And so although your warm up should speed up because you get application code coming through quick, all that extra compile work can maybe slow down your startup. And worse, if you actually hit a method that you didn't hit during the training run and you need to do a compile, your compile queue is already full of methods. It could be several thousand in a big archive. And we've hit this problem. So balancing the pre-compilation against the runtime compilation and evening it out to not slow down the startup too much is a balancing act. We're juggling with the timing and the how to do this. We basically have a switch where you can just either compile the hell out of everything, or delay compilation until the method's actually, there's demand for it, and then pull the profile data in. You're still better off because you've got profile data, so you only have to do one compile. So you go straight to compile code, but it's the timing issue that's at stake. That will be resolved when we can save the compiled code and we get the profile and the compiled code. We don't have to do all those compiles during startup. So when we get to 27 and we can just pull in methods, actually we'll have compiled code ready, and we'll really zip along, and it will really make a big improvement. And in fact, that's available in the Leyden repo already. We know this will work because we've already got it in the Leyden repo, which brings me to my plug for the day. There is a new Leyden early access release, the second early access release from the pre-main repo where we're doing all this work. So if you want to try this out, including saving and
That is the
restore
wrong.
of,
Sorry.
oh,
Sorry. I had it queued. And I've just completely pasted in the wrong link. Okay.
Yeah, anyway, there's a release out there that you can use to try this out. It's got all of these 3 JEPs all implemented. It's not necessarily guaranteed to be bulletproof, but it's fairly reliable. We're very happy with it. It's what we're going to push in production over for both 26 and 27. We'll be working towards putting this in. So this is something where you can try out and you can see how much gain you get from not just having the classes pre-linked, but having compilation profiles and compiled code. And you have the ability to pull code in straight away and use it, and also to recompile it if you need to without any delay. So what the 3 JEPs together really give us quite a big advantage. But we're still playing around with timing and tuning. You know, it's not all yet perfected. We're working towards getting the timing of things. We have actually done a lot of work on optimizing the compilation process. We've parallelized the queuing. We've got rid of some order n squared algorithms that are now down to order n algorithms. We've also done some preloading of the cache and pre-warming of the cache to mean we can get this stuff in quicker. So a lot of the stuff that were barriers to getting the most performance out of this, we've actually already optimized away. So we're pretty good in terms of performance, but it's really about the timing of the large scale orchestration of all these events that we still need to experiment. And on the other side, of course, the thing that's still experimental is experimenting with the training, which is what the users need to do.
Yeah.
What do you train and how do you train? How long do you train for?
Yeah, what's the optimum training strategy? You mentioned that the time to peak throughput will be reduced, which makes total sense. Do you see any actual impact on the peak throughput? Because I know with Quarkus, when we sort of started out, one of the things that really surprised us and I think our users as well was, you know, our initial thing was, can we boot fast? And then we realized that once we had booted fast, we were actually running faster as well. And that some of the things like method dispatching, that because of we were doing method dispatching faster, that actually gave us a throughput win. Do you see the same with Leyden?
So there's a mixed answer here, yes and no. I mean, the fact that you've got all those Lambda methods all there and pre-compiled will give you some benefits. It means Lambdas are dirt cheap. You don't have to worry about using Lambdas, whereas Lambdas are quite expensive. So there's a certain amount of reduction in work done. That won't necessarily help your peak performance, but it means you get to the peak quicker, and you can actually get some improvement in the performance from some of the optimizations available there. But the main thing that's going to be a problem here is that when we compile stuff ahead of time, we have to make allowance for the fact that the runtime might not be exactly the same. So one of the things, for example, imagine you train with a 200 megabyte heap, but in production you go for a 2 gigabyte heap. Because you're training, you're only simulating, you know you've got small data, so you don't need a 2 gigabyte heap. One of the consequences with the G1 garbage collector of doing that is that the garbage collector keeps track of regions and of references between regions. And the region size is dynamically scaled according to the heap size. So when you're doing a garbage collection check in a barrier to see whether this pointer in this object is pointing to an object in the same region or another region, you have to take different numbers of bits off the pointer to work out which region it sits in. Sometimes the region is it's 5 bits shifted off, sometimes it's 6 bits shifted off to give you the index for which region you're looking at. And as a consequence of that, the code you generate for a garbage collector barrier that decides whether we need to track this as a region crossing reference or not will work with a hard-coded 5 in the instruction or a hard-coded 6 in the instruction. If you compile the code with a shift of 5 and you run it on a machine that needs a shift of 6, it's not going to work. It'll say this is in a different region, even though it's not. And everything gets its knickers in a twist and it all goes wrong. So what we need to do when we compile the barrier code into an AOT compile method is pull that constant out of a constant record, a constant area that we've created in advance, rather than hardwire it as a number in the instruction. Now that means that instead of having a shift which has an immediate operand and is simple, we've got a memory load and then a shift. So that means that every time you do a field access, a field write, where you need to consider if you've got a region crossing in G1, you've got a slightly slower operation. Now, that was the first thing we hit, where we had to do slightly different code for ahead of time generation than we do for normal generation of compiled methods. We've got another situation to do with marking cards for which are dirty regions for some of the garbage collectors and so on. So there's a card table base for that we put in this constant area as well. So there's a few places where we're doing a little bit more work. We're doing an extra load. We don't have a constant in the code. That not only means you get slightly different memory access patterns and slightly slower because there's more cycles for a load, even though it's a hot area because we'll always be pulling things from there. It still slows down a bit. It also means that the code processing and identification of what's happening in the code in the microarchitecture in some cases is less efficient. We may need to do similar things where we use slight variance on the code generation strategy in the compiler to allow more flexibility in the production run environment, because you want to change the heap size. You don't want to have a fixed size heap, but as a consequence, we have to have slightly less performant code. So when you load these pre-compiled, heavily optimized methods, little segments of the code might still be a bit slower. But now that will mean that if you didn't do anything about that, your peak performance would be lower, because it's just 2 or 3% slower, maybe, if you're 5% if you're unlucky. Depends on what your code's doing. But what we plan to do is with this is why it's really nice having both a static ahead of time and dynamic runtime compiled JIT mechanism. We've got a VM that can do both here. We can have this pre-compiled code, but we can age it. So if a compiled method that we've pre-compiled and loaded has run for a while, eventually, after it's been in the VM for long enough, we can decide we'll take that out of service, we'll recompile the method, and then replace a new version of the method that's fully optimized using the dynamic information. And so that shift that's using a load for the shift index now switches to an inline shift. And then the other thing we had to do to use a PC relative access to a value, instead we absolutely jump directly to an address, rather than indirect through a jump table. Those will go. So there's an opportunity for us to use this code to get through warm up quicker, but still replace it with optimal code for the really hot methods where it will really matter. So it might be that maybe 20% of your preloaded code sits around, it's not run very much, and it's not aged, and it's not got rid of, but it doesn't matter because it's only ever called once. But the stuff you're calling all the time, we will take that and recompile it to absolutely tune the hell out of it again and get it back to peak. So we have a plan for getting to peak performance. Again, it's not been straightforward because we tried doing that and we were missing some things. There were some things that mattered that we weren't aging and didn't die and get replaced. It's a balancing act for how quickly you throw something away and how much work you spend to replace it. And it's a trade-off. So getting it right is tricky. And again, this is a tuning issue that we will be addressing in 28 and 29, and probably beyond 29 as well, actually. We'll probably find that there are things where we will have the ability to add more flexibility for usability, making it easier to deploy with different configurations. But then we can claw back the actual performance, and we still get a win in terms of startup and warm-up. And it's really a complicated trade-off. How much do you do? How much room do you allow? What do you take as a hit to get a temporary improvement by having the code early that you can then remedy later on? So it's a difficult juggling act, and it needs really a lot of experimentation to get it right.
Yeah, and I guess it's probably always going to need a little bit of user decision as well, isn't it? First of all, to make the decision to do the training run, and then to be giving some guidance on, actually, I'm going to be running this job for 2 months, so maybe.
And this is the thing we've been worrying about in the actual Leyden dev team meetings, because we've been worried, how do we make this usable? How do we make it possible for users to deal with this array of extra choices that are available and manage the process of running their application, training it, generating an archive, seeing what it does, and then making decisions about what benefit they're getting, and maybe using a different training strategy. And it's difficult. It's really hard to get those things right because we don't even know the answers yet. But the one consoling thing, this is what Alexei Shiplev keeps saying this in the meetings we have, the people we're dealing with who are using this right now are really our absolute power users or super users. They're the people who put perf onto their applications and look at flame graphs and work out exactly where all the time is going. They get JFR recordings and they analyze the hell out of them. We've got people who really understand how the hardware works, how the in many cases, like people like Sane, how our compiler works, what our JIT compiler does, or Francisco Negro, our performance guy. Okay, they understand the guts of the VM really well, but they understand the middleware as well. They know what that's doing. So we've got people at the moment, power users, who are giving us feedback where we can actually grapple with these issues. But in the longer term, we're going to have to get people who have less understanding of what the thing's doing to get the benefit from this. So we've got to make it more usable. So we're on a learning curve, our power users on a learning curve, but the long-term goal is to try and make it as easy as possible. That's why we've got 4 different mechanisms at the moment for ending the training run. Yeah. Those are the things right now. Which of those will be the ones that most people want to use? It's probably going to have to think very simple, like you just drop off the end of a run, or you maybe the command line option for some people. Although if your training runs 2 seconds, because that's all you run for, you drop off the end of a run anyway. If your program would run forever, you need to tell it to stop. So we don't know yet for sure exactly what we want, but we will be getting there by experimentation and by getting feedback. That's why we really want people to use it, to tell us what they like, what they can use, what are the problems with using it.
And that leads me quite nicely to my next question, because I was going to ask, what should people be using, be doing? so I guess it's using it and giving you feedback. So what's the best approach for someone who wants to start using this?
Okay, well, the latest EA release, which we have a link for in the chat, it's the best place to start in the sense that it's got the full capability, and if you really want to experiment, that's probably where to go. But there are actually capabilities in JDK 25 that allow you to create an AOT cache and then to consume an AOT cache with the cache linking and with the method profiles already preserved in your AOT cache. So you can experiment with this in JDK 25. That's the most stable, the most reliable stuff. Obviously, we've been very careful about that. But I would recommend if anybody really wants to see what they can get out of this, going for the early access release. The instructions about how to use that are on the front page. The README for the repo describes all the things all the levers you can pull, sort of what you get as a consequence of doing that. You've got to be able to actually run your application using the right set of arguments to actually build an AOT cache as a training run, and tell the app, either just have the application run in a sort of dummy mode where it switches off itself, or you can set some command line parameter to the main class which tells it to run for a while and switch off, or you can use the other options to control the thing to switch it off, and that will give you an AOT cache. And then you basically rerun your application and see what performance it gives you. Now, you get this file, an AOT cache file. It's whatever your name is, .aot, in your directory. And once it's created on that run, it's used by default from then onwards, unless you switch off using the cache. So it's sort of pretty automatic. Run with the create cache options, run with the use cache options. There's a few AOT -XX AOT something or other options that you provide on your command line. From Quarkus, you can actually enable those. I think there's already capability in the Quarkus plugin to do this for you. But that's not really what you need to do is actually measure at some point how long your application takes to get to the point where main is entered, how long it takes to get to the point where your server requests are being served at a reasonably high rate, so you're at peak performance. So you've got to have some way of actually measuring that and see what happens when you train on a given training run where you run the application a certain way. What benefit do you get? Now, there is a wrinkle here, and this is an issue that we wanted to resolve, and San is looking into resolving this. At the moment, the only classes that are capable of being saved in the archive, pre-linked, have their methods compiled and the compiled code reused are classes that are in the class path. As it stands with Quarkus at the moment, Quarkus loads application classes in its own class loader. And the way things are built just now, we need to know what the class loaders are doing and know that they're safe in order to make sure we don't do anything that invalidates the integrity of the JDK runtime or the JVM runtime. So we can only provide this archiving and restore capability for class path classes. And your class path has to have exactly the same things in the class path. You can add extra jars on the end, but you can't change the initial segment of the class path. So at the moment, if you try and optimize a Quarkus application, the only things that you will be training and getting pre-compiled code for and pre-linked classes for are the Quarkus classes themselves, which sit in the class path. Now, there is a modification I think can be made to Quarkus to allow the application classes to be loaded from the class path. So if you wanted to get this actually training and building pre-created content for your application classes, you'd have to use that variant run mode for running Quarkus. We want to be able to actually get the Quarkus class loader to be a known entity that Leyden knows about and trusts, and that it lives up to a contract and satisfies an API that's required for any of the known class loaders, the built-in class loaders, so that we can actually make Quarkus application classes play ball as well as the Quarkus runtime itself. So at the moment, if you're playing with the current thing, either you can adjust to get things in the class path, or you're just going to be training the Quarkus middleware, which will still give you a good advantage because Quarkus will get to its peak quicker, even if the application then will still have to go through all the normal startup and warm up that it does. So that's the only caveat. But basically, you build an archive and you run it and you see what benefit you get. So you need to be able to know, have some message comes out with a timestamp when you hit main, and have a message that comes out with a timestamp when you're or some way of monitoring your server where you can identify you're getting peak throughput, monitor the requests and see where it happens. And hopefully you should get things happen earlier. One of the things that you can do is play around with the archive and the training and see and get different things in your archive. Now, this is another area we've got a usability issue and we're working on it, but we haven't got a good solution yet. When you dump your archive, there's a whole lot of classes in there that have been pre-compiled. There'll be JDK classes, Quarkus classes. If you sort out your application in the class path, application classes. The only way you can identify what's in there is look at the log information, enable log information for the JVM, and look at this stream of log information that comes out of the build process that builds the cache. There's just been a new JEP added so that when a new issue of implemented in, I think actually in mainstream, that's therefore also in the Leyden EA release, which means that you can now dump the content of the AOT cache on startup. But this is a low-level dump. It tells you the memory layout of the AOT cache file. And in that memory layout, there's details of every single string, every single Java-lang class, every metadata class, every metadata method in the JVM model of the class base, all the lambdas, all that information. Every single thing that's in there is documented in enormous detail, and its layout in memory and its cross-reference to all the other objects is there. So there's this very detailed map of all the elements that are in your archive. And if you run in your production run enable logging, you can get that dumped to a file and you can get a log of the full archive contents. But of course, it's not very consumable. So one of the things that we're working on in our, actually one of our ex-Quarkus devs who's joined our OpenJDK team is working on, is actually building an application or a tooling using probably Java, probably Quarkus itself actually, to process this log and to build up a map of what's actually in that archive in a more abstract form, and then answer queries about what's actually in the archive. Which JDK classes have been pre-linked, which things are linked to what application classes are in the archive, which methods are being compiled at C2 level or C1 level, that sort of thing. So you're going to use this logging mechanism to identify what's in there and dump a log when we start the application or when we build the AOT cache, and then post-process it using some tooling that we're going to build. And that will be really critical. And we're really keen to get this done as soon as we can. We're working away at this as hard as we can, because clearly if you've built your archive and you run it, you can see that you get a speed up. If you go and change the training run, you get a different speed up. It might be better, it might be worse. You don't really know why unless you know what's in the archive and which things you're actually using. The second thing we want to do, as well as the map, the static map of the archive contents, we can also switch on logging during the production run to see what's actually being loaded, pulled in. Some of it's automatically pulled in because it's just assumed it's going to be valuable, like all the C2 code. But some of the classes are referenced and pulled in and others aren't because they're not needed yet. So we'll also get dynamic information about what's being consumed from the archive, and we'll extend the tooling to say what was actually in use and what wasn't used and when it was used, early or late. And then we'll do the same with the logging that's done for the training run. We'll keep track of what's actually being run during training, and we'll be able to summarize that. And you'll be able to see what was trained on, what went into the archive and what was thrown away, and then what was actually consumed. And with that information in place, then you'll be able to have a proper view of what the training is doing and how much benefit it's giving you. So this is the long-term plan. Again, this will happen over the next few releases. We may have something, we probably have some basic tools in 27. We'll probably have some better tooling in 28. In the longer term, we may stick with using the logging model because there's already a lot of log code in there that we use for development. We can use this to feed tooling, but it's a bit expensive. It takes time to write logs during runtime. We may eventually go for generating JFR events to a JFR file, a file stream, the way that JFR does. It's very efficient. It's very compact. We may be able to switch to that and then use either something that queries a JFR event log or mission control itself as another alternative to actually process that information. So we can use that as a way of analyzing events generated during training, during archive creation, during archive consumption. And that will give us an alternative way of doing it. But we're not sure yet, and we don't want to commit to JFR as the solution until we prototype tooling, just using our own Java tech that we develop or outside the project to consume the logs that we already have. So there is a solution coming for regulating this training process. At the moment, it's very much an experimental thing. Try running things, see what you get. One of the issues is that if you train your application and you train and run for a very long time, you might run all sorts of methods that actually run very rarely, generate compiled code for them, and then you come and because they've been C2 compiled in this run, pull them in and have them ready, but you never actually run them in most runs. So you can end up overtraining and having more stuff than you want. In some ways, it's quite good that we're only training by default on Quarkus stuff because almost all the Quarkus middleware is going to be called.
Yeah.
Not all the application stuff is going to be called. So having the application stuff in a class loader that isn't susceptible to training is maybe a good strategy for some apps. And your AOT cache that you use that is trained for the Quarkus middleware for one app might actually be just as valuable for another app because it's application neutral, or to a large degree. So there are lots of different strategies about what you train on and how long you train for that we need to investigate. And that's something we'd really like people, as far as they can, to experiment with. And as this tooling comes online, if they start to understand what's actually being trained on, why and how useful it is, we can get information for people to understand the application and then generalize over that and start to see trends and things that could actually be general advice that applies across different applications. So we'd love to have as many people as possible. And we're really desperately wanting to try and give you the tools as quick as we can to really do this properly so we can then help you and also help everybody else to make the most of this.
Yeah, that makes a lot of sense. And yeah, really interesting. And yeah, lots of good stuff now and lots of good stuff to look forward to. And I think as well, yeah, lots of opportunity for that really great collaboration of, in order for the JDK team to be able to give the best advice, they need to see these patterns in the field to and understand the pitfalls that people are discovering to share the best practices. So yeah, really interesting. Thank you very much for the update, Andrew. And
that's no problem. I'm really pleased to be able to just talk about where we're going and to also get across that there is a plan here and we've got things we want to happen in the future and we really want your help. That's the main thing.
Yeah. So takeaway, cool roadmap, stuff coming soon, stuff available now. Andrew wants your help. Got it.
Excellent.
Thanks very much.
Thank
See
you.
you all.